This is actually a redo of a web conference that we did that for some reason didn't get recorded properly, so we're redoing it here to post it up. So I wanted to get started here, and what we're going to do today is talk a little bit about EIQ Energy parallel system design and take you through some of the broad requirements for designing a system, what a system looks like in parallel, what the design considerations are, what some of the NEC limitations are, and hopefully if we can get through all this, we can hold all the questions till the end and then get to them then. So kind of give you a broad overview, first of all, of what actually, why you want to design something in parallel. I guess the biggest reason that we're finding is balance of system cost reduction. And this is really about being able to eliminate a number of the components that we currently use in series architecture and replacing them with parallel components from EIQ, namely the vBoost architecture. The vBoost architecture consists of a vBoost unit that goes at each module, as well as a vCom unit, which essentially replaces all of your combiner and recombiner boxes. Each one of those vComs can handle approximately 180 kilowatts, reducing that 180 kilowatts to a single set of electrical terminations between it and the inverter. The next is design flexibility. And because of the fact that we're no longer looking at voltage as a limiting factor, because the vBoost units are going to take that out of the equation, we'll talk a little bit more about that in a second as well. Your primary design consideration becomes just whether or not the modules are facing the sun and looking at the current ampacity being delivered by each module and making sure that your conductors are sized properly to be able to handle that current and transport it back to the inverter where it can be converted from DC to AC. A lot of issues come out. String sizing is no longer an issue because, once again, we don't care about voltage. We don't care about orientation because each individual unit is going to have its maximum power point tracking controlled at the module. So you can have modules with different orientations. You have modules with different angles of inclination towards the sun, all feeding the same inverter. So your design process becomes a lot easier. If you have to replace modules, halfway down your design curve, it's not a big deal. The vBoost basically takes care of all of that for you. Cost-optimized inverter selection. This is a big one that we find because of just some of these issues that we just talked about previously, of being able to have modules facing different inclinations in different directions, all feeding into the same inverter without affecting the production from each other. You can now take an array that you would have originally done utilizing several string inverters and put that into one larger central inverter, which is going to bring cost benefits associated with it in having to mount a single AC point, a single pad, and it's just going to be a lot quicker, a lot simpler installation, not just to install, but also to maintain throughout its lifetime. And lastly, because you're going to have this distributed power point tracking that the vBoost is going to deliver, your harvest is going to be much better. Depending on your environment that you're putting the system in, it can be anywhere from 5 to 30% more production over the course of a year. And as systems get older and the panels start to degrade, that's seldom uniform. So as they degrade, the array production actually goes down a lot more than it should for the individual degradation of each module. And the vBoost units help to recapture that and keep that array producing its maximum power throughout its entire lifespan. So let's get into a little bit about what the system does and give you a quick overview. We talked a little bit earlier about how the vBoost takes the voltage out of the equation. And what we mean by that is currently the way things are done in a series configuration is you take modules and you put them together in series in order to build up to the voltage that you want to be able to deliver to the inverter. This is a good way to get it done. but it brings along a set of baggage with it that we need to handle as we're designing these systems. The foremost is that all your strings have to be producing the same voltage because you're connecting those all in parallel. And if they're not producing the same voltage, you're not going to be delivering the power properly to the inverter. So in order to do that, you need to make sure all your strings are balanced properly, all your modules within that string are balanced properly, and any type of environmental hindrance, such as things like shading, maybe if a module gets some bird droppings on it, or if something gets, if one module gets dirty more than another, these are all going to affect your performance. When we go to an EIQ parallel system, the biggest advantage comes that you're no longer worrying about voltage. You're now just worrying about current. So you can actually put a lot more power onto each individual wire. And we'll talk about some of the math behind that a little bit later here. But suffice it to say that as we look at this, we can get a lot more modules onto an individual number 10 conductor. In a lot of cases, as many as 30 or 40 modules onto a single number 10, and have that kind of brought into a number 4 without having to have a junction box, without having to have a combiner box, and bring that on back to our VCOM box. So each panel becomes an independent contributor in the array. And what that means is that they're no longer affected by what's going on with the module next to it. So if one module gets some shading and the module next to that is still getting full sun, they're both going to be producing the maximum amount of power that they can for the level of sun that they're seeing at any particular moment in time. So it means that your least common denominator effect is not going to control the output of your array. And your design is going to go a lot easier because you don't have to worry about string sizing. You can basically just tile your rooftop if that's what you're working on, or tile your ground if you're working on a ground mount, and the vBoost is going to make sure that they're all producing the maximum amount of power, whether you have one on a wire or whether you have 40 on a wire. It's going to be producing the same amount of power. All right. Let's talk a little bit about the vBoost unit as a device. And this is very important to understand, because when we start talking about some of the NEC requirements later, it's going to become important to understand this concept. And what the vBoost is doing is it's taking power off of your module, and it's taking that power and converting it from a low voltage, higher current, usually 30 volts, maybe 8 amps, and it's going to bring that up to 330 volts. So you're doing about a 10x, in some cases, a 10x boost on that voltage. So what's going to happen, of course, is your current is going to drop by the same amount, by 10x. So that module that's putting out 8 amps is now going to be putting out 0.8 amps. And that's important to understand, because we're now trading this, right? We're trading the voltage for current, but we're maintaining the same power. And when we start looking at how we do our line sizing, this becomes an important element. So within that vBoost unit, it's taking that input off the PV module. It's providing real-time maximum power point tracking to that voltage input, to the power input off of the module. And then it's taking that power and through a OR-ing diode, putting it onto the bus. And that's important for two reasons. First of all, if anything happens to that module, if it goes out, if it's not producing power, if it's producing less power, it's not going to affect any of the ones around it because of that OR-ing diode. So that that power path stays completely independent of what's going on that bus. If it can produce power onto the bus, it does. If it can't, it simply doesn't. And it does not affect performance of any of the modules around it. It's also important to understand that the array then is now controlled by the inverter, because you'll see in this diagram there's no voltage regulation, and that's because the vBoost itself does not provide any voltage regulation. It has a maximum voltage output that it'll put out, but it allows the inverter to control what the actual voltage is going to be off the unit. So this way you're safe from the NEC perspective. You're never going to go over voltage. And as long as the inverter is controlling the voltage, the units are always going to deliver at the actual level that the inverter needs in order to get current to flow from that vBoost unit to the inverter itself. The other thing that the vBoost unit is going to be doing is collecting communication information. It collects all its telemetry information and it ships that off over the power line carrier, essentially over the DC bus. So just moving on here, the EIQ solution is providing everything from the back of that module to the inverter. And as you can see in this diagram here, we've got the vBoost units connecting to the modules, and then each vBoost unit connects to the other. And if you remember in the diagram before it, I'll just flip back here real quick, the DC bus goes straight through. So each unit basically forms the bus, the number 10 wire, which we're going to call the branch circuit, going into what we call the trunk circuit, the number 4. And we're going to take these number 10s, we fuse them at 30 amps because the NEC says that the most that you can put on to a number 10 is a 30 amp fuse. And we bring that into this number 4 wire, which then comes into our VCOM unit, and that is then connected into the inverter. All right. So if you get an idea, then as we start to build the array, we're just adding those VCOM units in approximately 180 kilowatt chunks, and then bringing them into your central inverter. So you're really limiting the amount of wire that you have running out from the array back to that inverter, maximizing its ampacity, maximizing its use, and really, cutting your costs in the process. So let's talk just briefly about some of the safety features that the vBoost system brings to the table. First of all, during construction, when you're putting the units in, there's no voltage on the bus, which means, of course, if there's sunlight out, the modules themselves are going to have a voltage potential across its terminals. But as soon as you plug those into the vBoost unit, the vBoost unit absorbs that voltage and blocks it from flowing into the rest of the array. And this means that when you're installing the system, you're truly just making mechanical connections. There's no power, no high voltage, no high current that's going to be present on any of the vBoost to vBoost connectors. The other is fire safety, because just the same way that during construction we have a safety mechanism built in not to allow that voltage to get onto the bus. The same thing during a fire. If there's an emergency at the location and emergency workers need to get onto the building, the system can be shut down so that no high, potentially life-threatening voltage is present anywhere within the array, because as soon as the boxes turn off, the vBoost units themselves, the most voltage that's going to be present is the voltage potential of a single module, and then it will only be present at the module. So we're going to greatly reduce the risk to those emergency personnel. And lastly, the arc fault detection and isolation. Obviously, this is becoming a bigger and bigger issue as the code starts to adopt provisions for arc fault protection. And the vBoost system allows for facilitations of those new requirements going forward. So let's talk a little bit about what the system performs like, and just to kind of give you an idea of what the performance vectors are for a vBoost parallel system. First of all, it's important to understand that this power, this increased harvest potential isn't coming from magic. It's coming from the fact that we're distributing the maximum power point tracking out to the individual modules. So it's really all a function of better being able to allow each individual module to consistently produce as much power as it possibly can as an individual unit within the array and deliver that power to the inverter in the most efficient manner possible. And by doing this, you can see here that we're going to get a number of factors that build together in order to get the increased production story. So, for example, there's a couple of points available for inverter efficiency. And what we talk about by that is being able to drive the inverter at a consistent voltage that is right within that inverter's peak efficiency range. Once again, the inverter controls the bus, so you could simply set that inverter to whatever voltage it's most happy at, and it'll just sit there all day long. Likewise, if clouds come overhead, the clouds are going to affect the array in a varying degree. Some modules are get affected more by cloud cover, others less, obviously depending on the cloud cover. But nonetheless, it's always something that's going to generate a lot more mismatch than what's there on a pure sunny day. And that's power that we get back. And in certain cases, it could be as much as 7%. Soiling, the same thing as cloud effect. Soiling rarely happens uniformly throughout the array. And if that soiling happens in any way that starts to generate mismatch, we're going to mitigate that effect. And that's also worth a couple points on most systems. Voltage drop, this is a higher order effect that starts to happen as your arrays get larger. And because you're controlling the voltage from a central maximum power point controller in a central inverter, it's going out and it has to drive that voltage through very long lines that have an effect of voltage drop. They get driven from one set of modules, one string, to another set of modules, another string, that's sitting in a different spot within the array. Usually the two far corners are the best example. And if you're setting a maximum power point that works for that first string, then the string that's all the way out there in the corner is going to have to drive voltage a little bit higher in order to get power back to that inverter, which means it's going to be a little bit further off of its maximum power point than the one that's closest. And the distributed MPPT capabilities of the parallel solar solution from EIQ is going to solve for that problem as well. And that's also worth a couple percentage points. We also have temperature mismatch. Temperature mismatch occurs across an array when you have things like, for example, wind that comes and hits the side of an array, cools down one side more than another. It also happens because the temperature coefficients of modules often vary a lot more than their IV curves. So that's also increased power that can be harvested if you have a system like the vBoost system in there that can take advantage of it. Mismatch, once again, this is either stuff that comes from the factory as far as the modules not being perfectly matched, or something that kind of builds up over time as part of the degradation of the modules. And we also recover that. Shading, of course, is probably the biggest effect. In a parallel vBoost-enabled system, if you have shading that's affecting a single module, that could severely limit the power production for that entire string. With the vBoost in the equation, it's not going to do that. That individual module that's being affected by the shading will, of course, produce less power, but it won't necessarily produce no power. And the modules that are around it will continue to produce as much as they possibly can, so there'll be no effect on them. So, in the aggregate, you're looking somewhere between a 5 and a 30% or above power harvest increase by using a distributed MPPT solution such as the vBoost Parallel Solar. So let's now dive into the design criteria, and let's talk a little bit about some of the terminology. We steal a lot of this from the lighting business because, frankly, it's kind of the same concept. If you think about the vBoost as a ballast box, you can kind of see this analogy play through. Each individual vBoost is connected in parallel to the one next to it, and that string of vBoost creates what we call the branch. The branch circuit is running on a number 10 wire, and therefore the number of modules is limited by the ampacity of that number 10. Each one of those number 10 branches comes back and feeds into a trunk line that gets connected with a set of MC4s through an inline fuse that's fused at 30 amps. And that number 4 wire can then take however many branches it can carry in order to maximize its ampacity, which we'll get into is about 96 amps. And if you're maximizing each trunk, you're probably doing about 4 branches per trunk. So if we look to the NEC for guidance, and we can take a look at a little bit here about what the NEC has to say about these things. The NEC says for number 10, I can have up to 55 amps on a use 2 wire. And for number 4, I can have up to 140 amps. Now, obviously, we have to go through all sorts of kind of downsizing on these numbers. But this is ultimately what these conductors are capable of being able to handle. And we'll get into a little bit about why that matters here in a second. So let me move on to the next slide, and let's talk about what the actual math looks like. So if I'm looking at a number 10 branch circuit, and you know, when we're talking here, basically Ohm's law becomes our guiding principle, and that is current equals power divided by voltage. So that little equation is going to solve for everything that we need to know in this particular exercise. A couple of variables that we need to just settle on earlier. Obviously, you could use whatever module you want to use, but for the purpose of the math here, we're going to use a 220-watt module. And we're going to assume that we're running our inverter at 330 volts, which is a pretty good assumption. Most inverters seem to want to run at that level and do so very efficiently. And therefore, we're going to look at our number 10 and say, well, what's the maximum current capacity of our number 10 as we derate it? And the answer is 36 amps. But as we know, the most we can fuse a number 10 is 30 amps. So we're going to look at putting a 30 amp fuse on that number 10, knowing that we have plenty of headroom there. Because as we saw from the previous one, we can actually take 55 amps, we're fusing it at 30, and we're going to run it at derating off that 30 amp fuse of about 24. So if we look at that math and you say, okay, what can my number 10 take? Well, if I have a number 10 wire and I'm running it at 330 volts and I'm looking at a 220-watt module, if I ran 22 modules, I'd have 14.6 amps. So that just kind of gives you an idea for how that math gets done. And likewise, now I know, okay, well, if I have 14.6 amps coming off each one of those number 10 branches, I can have 6 of those feeding into my number 4. And the math works the same way. I take those 6 branches, each one putting 14.6 amps onto the branch, onto the trunk rather, gives me a total of 87.6 amps. And that's going to drive 29 watts. So you got about 30 kilowatts going on to each one of those number 10 wires if you're going to run it at its close to its maximum capacity. Now, likewise, the design math, if we go and look and say, okay, well, what is the maximum number of units that I can get onto a line? Well, once again, I'm going to assume 330 volts is what our operating voltage is. We've got a 220-watt module, and I'm going to take that 220 watts, divide it by 330, right, going back to the Ohm's law calculation, and that's going to give me 0.67 amps for each module. Now, it's important to understand that that 0.67 amps is the theoretical maximum power, maximum current that module can produce onto the bus at 330 volts if that module is producing 100% of its nameplate. So there's going to be very few times in its life when it's going to produce maximum to its nameplate. But still, that's what we're going to use to define our system and to design it. The other thing that's important to understand is that each one of those units also is fused. Each one of the vBoost units is fused at 1.5 amps and current limited at 1.2 amps. And we'll get into that calculation later, but just to understand there's a lot of backdrops there that are going to protect that unit from going crazy and putting a ton of amps onto your line and potentially causing problems to your copper plant. Now, continuing with the calculation, if I say, okay, I got a 30 amp inline fuse, I want to derate that back 20%. So that 30 amp fuse, I can put 24 amps on. All right. So if I take that 24 amps and I look and I say I've got 0.67 amps for each vBoost, I'd simply take the 24 amps, divide it by the current capacity for each individual vBoost, 0.67 amps, and it gives me a total of 35.8 modules, which is the max that I could get onto that particular branch. So in this case, of course, I'd round down to 35, and 35 would be my answer for how many modules I could get onto single number 10, utilizing this particular solar module at 220 watts. Now, let's for a second take a look at the NEC view. So if I have a number 10 conductor, the maximum ampacity of that number 10, before I derate it for anything, is 55 amps. So in its best life, it can handle 55 amps. But we wouldn't want to have to handle that ever, or if at all, for long. But the point being is that each vBoost unit is also fused at 1.5 amps, which means it can never produce more than 1.5 amps onto that bus. So if I look at that and I say, okay, if I have 55 amps maximum, and I have 1.5 amps that the maximum current each one of my vBoosts can produce, if I divide 55 by 1.5, I come out with 36.7. So as long as I'm under 36 devices, I'm never going to produce more current than that conductor is capable of handling. And once again, this calculation is far from any type of reality that we would ever see, because the maximum current that we just calculated that this module can produce is 0.67 amps. And once again, that's if it can produce 100% of its nameplate. So let's take a look now at that number 4. So each one of those number 4 wires, which is the trunk, likewise is being fused at 125 amps. We take 80% of that, which is 100 amps, and say, okay, how many can I get in if I was doing 100 amps, if I was doing 0.67 amps for each one of my vBoosts? So I take 100 amps and divide it by 0.67, and I come out with 149.25 devices. So that's saying I could have roughly 149 vBoosts on each one of my trunk circuits. So that's kind of the math behind it. Let's just kind of take you through what a site looks like. And you can kind of see here, this is a recent site that we did. The site was a megawatt in size. It was challenged from a geometric perspective because, as you can see, it's not really a perfect square. There were a lot of long runs that needed to be accommodated, runs that were probably longer than you would want to see for purposes of voltage drop and I²R losses. But this was relatively easy to design utilizing the vBoost system because, once again, each individual vBoost is always delivering whatever voltage it needs to provide for that inverter to have power flow from that particular vBoost unit. So what that's saying is the vBoost unit all the way up here in the corner, my inverter here is running at 330. This vBoost unit all the way in the far corner might have to run, you know, a few hundred feet, maybe 700 feet to get to that inverter. So there's going to be some voltage drop there. And if the voltage drop, let's say, is 10 volts, what that's going to mean is that this vBoost unit out here is going to be needing to put at least 340 volts onto the bus for the inverter to see 330. And that happens automatically within the vBoost architecture because there is no regulation at the vBoost. It simply boosts the voltage to the point where power flows from it to the inverter. And it's kind of the simple magic, simple elegance of the solution, if you will, to allow power to constantly always flow from the source to the sink, of course the sink being the inverter. So in this design, the other thing to note is that you see the blue and the green here. We actually had 2 different module types that needed to be accommodated, running into a single inverter, running a single channel of input. So what our units are able to do, once again, is to make sure that the modules that are in blue here, even though they're a different power rating than the modules in green, are all able to coexist on the same system and make sure power always flows to that inverter. So if you kind of take a look at what this site looked like as it installed, you can see here the vBoost units that were mounted underneath the modules. And you can see how they, there was a simple elegance to how they were architected into the solution. There's just basically one vBoost on every other cross member going down here. There's one set high, one set low, and then the modules are actually grouped. We had 4 modules going into each one of these vBoost units here. Likewise, you can see here how that went. We had, here was the high row of vBoost, here's the low. Then we had a couple stragglers down here that we had to take just because the racking wasn't necessarily optimized for how the modules were laid out. But you know, the vBoost solution was flexible enough to be able to manage that. But the other important thing here to note is that each one of these is exactly the same structure. So as they fed into that trunk line, really all the electricians had to do was just recreate that same wiring diagram block after block after block throughout the entire array. And you know, you've got an idea of what that looked like from earlier, where we have the vBoost running up and running down, and the module is just simply connecting into each one the same over and over again. And you can see here, this shows how they're all kind of coming back into the various vComs throughout the array. We can see in here that we have 9 vComs running. This is a little bit more than we would have had to do for a standard solution. If we were doing a standard 1 megawatt block, you probably would have done it with just 4 vCom units. But because of the fact that we had a pretty wide dispersion in this array, we did it with more in order to be able to have less current coming back from each one of those vCom boxes through the distance that it had to run to get back to that inverter. So you can see here in this diagram how the actual vCom mounts. It's mounting behind the rack. Here's your racking. The vCom box is mounting back here. Its lines are coming up from both from the array and from the ground. And I've got some pictures here so you can see what that actually looks like. As you can see here, these are the outputs that are going back to the inverter. And in this case, we ganged 4 500 MCM aluminum lines for each vCom and ran those back to the inverter. And you can also see here, these are the input channels for each one of the trunk lines coming back from the array. So this kind of makes it a little bit more visual as to what's actually happening and what that looks like when you get out to the field. You can also see in here the 125 amp fuses, which are lined up down here. In this case, we have 6 125 amp fuses. And then that power is all ganged up into these two sets of contacts here in the box. So when you sit down and actually do your current calculations for all your various branches and trunks, this is what it looks like. And I won't get into this in too much detail. I mean, I think the numbers kind of speak for themselves. But the point being is with this document, your inspector basically has everything that they need in order to kind of look through and make sure that you've done your math and you've done your design properly to make sure that the array is operating in a safe manner and that all the conductors are being managed within the NEC guidelines. A couple just looks here on how a design would work with installations that might be a little bit difficult without a technology like the vBoost. So for example, this solution has 3 different rooftops, and without EIQ, they were being routed to a set of at least 6 separate inverters, but in actuality, it ended up being more like 12 inverters. With the vBoost system, they were able to change this into a single inverter and run all that into one, even though they're all, as you can see, have different orientations. We have some southeast, some southwest, some south, some north. It's really all over the place. And they were all able to run right into the same inverter. And this is actually like right along the equator. So you know, the orientation didn't have as much of an effect. But still, it would have required more inverters without us. So it helped to really solve a lot reduce some of the costs in the upfront inverter buy, as well as on ongoing maintenance. Another site kind of looks a little bit similar here. We've got different orientations. You've got some rooftops with different facings. You also have some carports. They could be at different inclinations. Some may be running at 30, some may be running at 20, some may be running at 10 degrees. And once again, with the vBoost system, these can all feed the same inverter without having to worry about compromising on any of the power production. So just some ideas. If you see these types of scenarios as you're going through a design, you should probably be thinking about a parallel solution. You probably should be thinking about taking a closer look at the vBoost for that particular install. And just kind of running through some of the balance of systems cost reduction numbers here. Just real quickly, it's important to understand that the vBoost is providing a complete solution from the back of the module to that inverter that is ETL certified. So everything in between the vCom and the vBoost is all a mechanical connection. And that really drives a lot of the savings, because what we're doing is we're really taking labor that was of a much higher class, much higher cost, and we're bringing that labor into a different level. We're taking something that needed to get done by an electrician, and we're allowing it to be something that can be done by somebody who can make a mechanical plug connection. Depending on what the job specifics are that you're working on, are going to drive what your actual savings and what your actual labor class is for each one. But suffice it to say that you're going to have a lot more flexibility utilizing the vBoost solution. And just kind of looking at the savings, we actually took a look at this this job that we originally looked at here, which was the 1 megawatt one, and we had a quote that was without EIQ, which was around 69 cents a watt. And then we looked at that quote with the EIQ, and as you can see, there was a significant amount of savings here. The actual hardware cost was around 35 cents for the vBoost solution. Mechanical was about a penny, and that was the whole installation of the vBoost and all of the DC wiring. And actually, they had 3 guys who had never done solar before come in, and they did that whole array in under 7 days. And you also still have the electrical, obviously, all the AC that needs to get done, and those final DC connections from the vCom boxes to the inverter, and that was about 15 cents a watt. So in total, we took a 69 cent a watt job and reduced it down to 51 cents a watt, including the cost of the EIQ hardware. So in this case, we actually saved 18 cents, even after our costs were included. Plus, we're able to bring all the benefits of distributed MPPT, monitoring, and all the other benefits that you get from utilizing a parallel solar solution. So let's talk a little bit about that monitoring and O&M stuff. We've got each one of our vBoost units, as we talked about earlier, is providing its actual telemetry information. So for every 5-minute increment within the day, you can see what each individual module is doing. And of course, this is very important because you're going to be able to spot immediately where there's problems. And the graph that we have up here on the screen is kind of showing what it looks like. I'm plotting different vBoosts against each other. So now I can see how they're performing relative to one another. And in this particular installation, I actually have 2 technologies. And you can clearly see the bands of one technology versus the other, and kind of what their performance is throughout the day. And that is the presentation. So I would ask if we have any questions. Now would be the time to answer. But I believe that since we're doing this as a makeup, that we don't have anyone on the line. So I can talk to some of the things that we had from our lab. I think some of the questions that came up were around how the vBoost works as far as being able to boost the voltage. And suffice it to say that works is that it takes the voltage coming off the module and simply provides a pure voltage boost to the array, or to the modules that are feeding into it, and takes those modules and allows them to output whatever voltage the inverter regulates. So if the inverter regulates the bus at 335 volts, each vBoost is going to float to whatever voltage it needs to float to in order for that inverter to see 335 volts from that individual vBoost unit. So if that unit needs to go a little bit higher, it will. If it's right on target, then it'll flow to that point. But it's always going to flow to wherever the inverter drives it. So the inverter is still in control. So what you really need is you need an inverter that can drive in either constant voltage mode or have an MPPT window that's narrow enough, usually about somewhere between 2 and 5 volts, so that it's not constantly throwing the voltage around on the array. So that's it for today. Thanks everyone for your time and attention. I appreciate it.